The field of cryptography had improved significantly in the early 20th century, with most of the advancements concentrating on symmetric key cryptography. Ensuring privacy and security is the most well-known cryptography issue back then, which involved preventing illegal data extraction from communication through unsecured channels. So how could two people who have never met have secret communication over a network and agree on a secret shared key without letting the eavesdropper crack their information? In 1976, Whitfield Diffie and Martin-Hellman revolutionized the field of cryptography when they published their paper, New Directions in Cryptography, which explained the mechanisms of a new system that would become known as the Diffie-Hellman key exchange and solve the issue in the security of the crypto system. In order to have a secure key exchange, the computation must be complex to avoid an attacker from recovering the secret key and cracking the crypto system. The security of the Diffie-Hellman key exchange is based on one-way functions. It means that it is easy to calculate in one direction but much harder to calculate in the reverse direction. This is known as modular arithmetic, which is also known as clock arithmetic, or x modulo p. However, we must substitute 0 for 12 in the clock because the remainder begins at 0 and increases by 1 each time. To find the solution of modulo using a clock, we need to take the given units and crop them around the clock with the given modulus units. And when the rotation of the given unit stops, it is the solution. But in order for the process to work, we need the prime modulus and then we need to find its primitive root that has no common factors and has the property that when raised to different exponents, the solution is distributed uniformly around the clock. This is called the generator. Solution is equally likely to be any integers between 0 and the given modulo. If we raise the generator to an exponent x, the reverse procedure is hard. Say given the answer to modulo, we need to find the exponent that needs to be raised to. This process is called the discrete logarithm problem. The time it takes to reverse a one-way function is its strength and using prime modulus. It is hard for the attacker to know the key as it consists of hundreds of digits long. To further understand the concept behind Diffie and Hellman public key cryptography, let us first discuss its mathematical model on how to ensure secure communication over unsecured networks. So before starting, the communicating parties must agree to publicly share two large prime numbers that is called the generator and the prime modulus. Take note, the G is the primitive root of P and it is accomplished by sending the key over a secure route in advance, such as private courier or registered mail. Next, each party needs to select a large private random number x sub a and x sub b, but is less than to the value of n, then calculate y sub a using y sub a equals g raised to x sub a modulo n, while the other party calculated y sub b using y sub b equals g raised to x sub b modulo n. Then send the result publicly with each other. Here comes the hardest part of the process, which is taking the other party's public result and raising it to the power of their private key using k sub a equals y sub b raised to x sub a modulo n and k sub b equals y sub a raised to x sub b modulo n. Now, let us proceed to the example. First, Alice and Bob need to publicly agree to share two large prime numbers, a generator g equals to 5 and the prime modulus n equals to 23. Next, Alice needs to select a large private random number, x sub a equals 15, and Bob will also select his own private random number, which is x sub b equals to 19. Then Alice will now calculate y sub a by raising her private random number to their agreed generator, and prime modulus y sub a equals to 5 raised to 15 modulo 23 equals to 19. On the other hand, Bob will now calculate y sub b with the same step as Alice did. Y sub b equals to 5 raised to 19 modulo 23 equals to 7. Then, they need to send both or their result publicly with each other. After obtaining each party's calculated result, they will now raise it to the power of their private key. Alice will now compute her secret key, k sub a as follows: k sub a equals to 7 raised to 15 modulo 23 equals to 14. And then Bob will solve his k sub b as follows: k sub b equals to 19 raised to 19 modulo 23 equals to 14. And here it is. they will come up with the same answer and the key exchange is complete. Diffie-Hellman key exchange not only limits its participant to two parties but can also be used to create a shared key for a larger group of people. This process is called Diffie-Hellman multi-user crypto system key exchange. It works in the same way with the two parties, but with the exception that more rounds of calculation are required for each person to contribute their secret number and arrive at the same shared key. The information is also sent through unsecured network, just like the two parties process of Diffie-Hellman key exchange, but not enough for an attacker to compute the shared secret. The difference of this with the two parties is that the technique of exchanging keys is called multiple shared keys, instead of using a single combination of private keys. Parties can produce multiple shared keys while exchanging pairs of their public keys. Diffie-Hellman has a different style of shared key in the process. It is either a single key or combination to ensure security with multiple parties. Sometimes, additional keys are needed to obtain the shared key, and can be computed by multiplying the base keys with a different combination called extended keys. Then the participant can now calculate the overall number of shared keys at any given moment in exchanging keys and obtain the same answer. Based on the study conducted, number theory was not only essential in studying, but it also has real-life applications. Under this subject, Diffie-Hellman key exchange protocols were discovered, which is the public key cryptography that involves two parties, as well as the multi-user key exchange that involves a larger group of people. The complexity of solving the discrete logarithm problem in the key exchange will be difficult for the attacker to easily obtain their secret key and crack the crypto system. That's why the Diffie-Hellman key exchange process makes the exchanging of information secure even in unsecured network.